12s, welcome to science, and of course today we're going to carry on with organic molecules. Last time we looked at naming, so now we're going to look at the properties of organic molecules, and here we're really talking about physical properties, not chemical properties, so it has nothing to do with the reaction, it has all to do with boiling point, melting point, etc. Okay, so the first thing we're going to do is we're going to see if you understand or at least know something about the terms I have. So there's 6 terms. I want you to quickly have a discussion and see what you know about these 6 terms. So I'm going to give you 2 minutes to see how much of these terms you know. So are you ready? All right, your 2 minutes start now. Grade 12s, let's see how you did. Now remember, if you look at these, all these terms should be ones that you remember from grade 11. So let's just see how you did. Okay, and here we're going to look at general what they mean. Intermolecular forces, remember, are the forces or the attraction forces between molecules. Okay, so here I'm not talking about your covalent ionic bonds at all, though in organic it's all covalent because that's intramolecular or interatomic. Here I'm talking about the forces that keep the molecules as a liquid or a solid or a gas. Okay, so it's between the molecules, and these are the van der Waals forces. Okay, which of course we can split up, which we'll talk about in a second. Now remember, hydrogen bonds are a special intermolecular force, and it only happens when you have a hydrogen atom bonded to a small, so it's got to be a hydrogen atom bonded to a small, highly electronegative atom. So, and that would be things like oxygen, nitrogen, and fluorine. Okay, those are the ones we'd use. Now, for organic chemistry purposes, we're talking about oxygen. So when we look at hydrogen bonds, we're looking at the molecules that have oxygen and hydrogen in them, that have the hydroxyl group or the carboxyl group. Okay, so that's what we're looking at. Now, boiling point and melting point, these are, my gut feels you're going to get one of these definitions, probably boiling point at this point, because it was in the grade 11 final exam last year and the matric final exam last year. I think it's quite important, but be careful here, because this is a definition that you tend to get a little wrong, because your boiling point is when it turns from a liquid to a gas. That's very general, and that's acceptable for a junior, for a grade 8 to 9, but you've been learning since grade 10 that boiling point is the temperature, okay, at which the vapor pressure of the substance equals atmospheric pressure, okay? And now I'm doing all of this in great shorthand. It's wonderful. All right, so it equals atmospheric pressure. That's really important. There's a couple of key things: temperature and vapor pressure equal to atmospheric pressure. Okay, so those are the first things. Melting point, and melting point is probably the easiest one because it's the temperature at which a solid becomes a liquid. Okay, so it's the temperature at which a solid becomes a liquid. That's easy. Okay, now vapor pressure is an interesting concept, and it's going to come up because they like to try and confuse you between boiling point and vapor pressure. Vapor pressure is the gas that when a liquid evaporates, there's a vapor that sits on top of the liquid. It's the pressure that that vapor exerts. So if we write it down, okay, it's the pressure of the vapor of the substance at equilibrium, okay? So of the substance at equilibrium. Okay, but of the substance at equilibrium in a closed system. Okay, it's got to be a closed system. Now we haven't done equilibrium yet, but it's very important that it's a closed system, so it's got to be, it's not allowed to evaporate. Okay, that's what we're talking about. Now, viscosity, I hope you don't actually have to get to define, but I'm doing it to be thorough. Okay, viscosity is how quickly or how slowly something moves. So water has a low viscosity. It moves really quickly and easily. Oil has a high viscosity. It takes longer to move. And the thicker the oil, the more sludgy it is, the higher its viscosity. Okay, so that's nice and simple. Now, what we need to do is we're now going to look at the relationship between intermolecular forces and boiling point, melting point, vapor pressure, etc. So we need to define these intermolecular forces. So now we're going to look at the fact that we've got to look at the things that affect the intermolecular forces, okay? And they are things like chain length, and by chain length, grade 12, there's two ways we can change it. By changing the number of carbon atoms, which then means that the molecular mass changes, okay? So that could mean that I'm going from butane, comparing it to ethane, or I've got octane, comparing it to methane, but I've got the same sort of chain. It's just one long chain, but I'm changing the molecular mass, okay? The second way I can do that is by changing the number of branches, so going from butane to propyl, methyl propyl. I'll get that eventually. Methyl propane. There we go. I got it. It's a big mouthful for me. But what that means here is that the mass is constant. Okay? Now, the size of the molecule absolutely plays a role in the intermolecular forces because that's got to do with surface area. So when we have a greater surface area, there's more contact. The more contact we have, the greater the intermolecular forces. That's really important. And remember, Newton's law of universal gravitation still applies to molecules, just on a much smaller scale, but it still applies. So bigger molecules will have a greater force of attraction. But the force of attraction they have is also determined by their functional groups. Now, this one is really important. You've got to know what the functional group of different molecules is. So when you look at different molecules, okay, and I'm trying to find a page which has gone walkabout. Okay, now the type of functional groups we're looking at is, and I'm just going to quickly find it while we talk, is remember that you have alcohols, alkenes, aldehydes, etc., and all of those have functional groups. Now those functional groups, I'm not doing well here. No, where did it go? Found what I was looking for, so I have my slide. And now what's important with these functional groups is you need to be able to identify the actual van der Waals forces in them. So to remind you of what you learned last year, van der Waals forces can be broken up into two types, London forces and dipole-dipole. London forces are between non-polar molecules and they are very, very weak. Dipole-dipole are slightly stronger than London forces, but we have to have a polar molecule with them. And then, of course, we have hydrogen bonds, and hydrogen bonds are the strongest. We find them in polar molecules, but what's important about the organic is there must be an OH bond in there somewhere. So it's either with the hydroxyl groups in the alcohols or the carboxylic acids with the carboxyl group, okay? So now, where do we find them? So London forces are found, okay, between, I'm trying to get rid of my box now. Okay, so London forces are found between our non-polar molecules. Let me just get rid of the black that I put all over it. All right, and our non-polar molecules are alkanes, alkenes, alkynes. The bond between carbon and hydrogen is considered to be non-polar. It's so slightly polar that we can ignore it. And also because of the shape of the molecule and the way it bonds, they're non-polar molecules, okay? So we remember that. Our van der Waals or our dipole-dipole forces, okay, are found between, what? Oh boy. Okay, so there we go. Aldehydes, ketones, esters, and the haloalkanes. How strong those dipole-dipole forces are depends on the molecule. Esters, if they become very big, tend to start to look non-polar, so their forces tend to be a little bit smaller. Haloalkanes have got halogens in that makes them very polar because of the electronegativity difference. Ketones and aldehydes with the oxygen, it also depends on positioning, okay? But they tend to have the dipole-dipole. But then the one with the hydrogen bonds, those are our alcohols and our carboxylic acids. These ones are really important. Now, what you need to remember here, because this comes up often, is an alcohol generally will make one hydrogen bond, okay? A carboxylic acid can make two. That's because of its structure. And the thing with the carboxylic acid is that it does this. So we have the OH like this, and then we have the double bond oxygen, okay? When another hydroxide comes along, so let's take that away because I want to show you. Well, another alcohol comes along, okay? And let's put it over here. Now I'm going to put it on backwards. What happens is we have the OH over here, and we have the double bond oxygen over here. So we can form a hydrogen bond there, and we can form a hydrogen bond there. So there's two places for the hydrogen bond to happen. As soon as that happens, the intermolecular forces get stronger, more energy is needed to weaken or to overcome those forces. Please be careful with this section. When we talk about boiling point, melting point, etc., we're weakening intermolecular forces, not breaking them. Okay, please, this is a wording thing. It sounds quite silly, but I'm still getting used to it in that your examiners want you to say that you're weakening the forces or you're overcoming the forces, but you're not breaking them. Because it's not like a covalent bond where you're breaking a bond. You're actually separating them. You're just giving them more energy so they move away from each other. Okay, so that's really, really, really important. I have given you a lot to think about. So now we've got to take everything I've just done with you and we're going to have to put it into practice. We're going to have to look at some problems, okay? So we're going to take a short break, and when we come back, we're going to tackle some problems, okay? So I'll see you just now. Right, grade 12s, I really hope you are ready to tackle this. So now I have a problem for you, and we have a table that gives you the boiling points of 3 hydrocarbons, A, B, C. So there's a whole bunch of stuff here. This is why the naming from last week is so important. And then I have a whole bunch of questions. So there's 4 questions we're going to want here, okay? So I'm going to give you 3 minutes to do as much of this as you possibly can. Okay, so you're going to look at boiling points. This has to do with intermolecular forces, maybe a little bit of what we did last week, but it all goes together. So you're going to have 3 minutes. Okay, so I hope you're all ready. The question's I will move it up in a little bit for you to get the last question. A little way into it, but I'm going to give you 3 minutes, and your 3 minutes is going to start now. Okay, grade 12. So now we're going to look at this, and I'm hoping some of you picked up the mistake in the question. And this is really important when you read this, because now we're going to go through this, okay? Is if you look at my question over here. Oh, no, that's white. You can't see that. Okay, so let's undo that, because that doesn't help. But over here, can you see there's like a little O with a line underneath it? Well, that could maybe mean I was looking at maybe a ketone or an aldehyde, but actually this was supposed to be a triple bond. Okay, I do apologize, but it's all right. You probably didn't get too far with the rest of the question anyway, so it's all right. Don't stress about it. Just be careful with something like that in an exam. Okay, you can't actually deal with it with the way that molecule was written. So it should have been a triple bond, but that's okay. Now, with a question like this, whenever you get a table like this, grade 12s, what you need to look at is go, what did they change? Because we can only compare boiling points of substances where they change one thing. So they change the functional group, or they change the molecular mass, or they change the chain length, or they change something like that, but they can't change everything. Now, over here, this molecular mass is relatively constant. It's not completely constant, but that's also because we keep taking hydrogens out. Because if you look carefully, each of these compounds have 3 carbons in the longest chain. So we have an alkane, an alkene, and an alkyne. Okay, so this is only single bonds. So this has got a double bond, and then it's got a triple bond. They get smaller in mass because we're removing 2 hydrogens every time. That's not that much of a big deal. So what this particular table is telling me is how the boiling point changes because of chain, well, not because of chain length, but because of functional group. Okay, so it's got to do with the double and the triple bonds here. Okay, so first thing they ask is to write down the series to which A, B, and C belong. So A, all right, are our alkanes. So this is like what we did last time. Alkanes. B are my alkenes. Now, they're not asking you to name the compounds. They just want to know which family they belong to. And C is our alkynes. Now, the next one's a reading problem, because now they say place the compounds in sequence according to decreasing strength of intermolecular forces. If the intermolecular forces get weaker, the boiling point gets lower, okay? So the stronger the intermolecular forces, the higher the boiling point. The weaker the intermolecular forces, the lower the boiling point. Now, if we look at these boiling points, they're all in the negatives, okay? They're all in the negative, so it's minus 23, minus 48, minus 42, okay? Now, according to this table, minus 23 is my highest boiling point, okay? That's hotter than 42 and 48. So that means C has my highest boiling point. So it goes C. Then it's going to go to, and we go back to our table A, because that's minus 42. And, oh, no, let's just write it all the same the whole time, shall we? Just because it's easier. And then that means it has to go, oh, no, 42 is bigger than minus 48. Sure. There we go. So we've spelled cab. Don't worry if it spells things. The examiner might have just had a moment when they said it. Now, name the intermolecular forces. Watch here, this is becoming a big thing. Name the intermolecular forces that exist between the molecules in these compounds. Guys, these are all non-polar molecules. These have London forces, okay? Some of you may have learned these, it's just another name for it, as dispersion forces. Either is correct. You cannot stay here. Van der Waals. Okay? We used to accept Van der Waals. It's too general. Okay? Here they're specifically wanting to know, is it London forces or is it dipole-dipole? Okay? What are the forces? So Van der Waals is too general. This is London. Now we get to the fun question. Explain the difference in the boiling point. Okay? Now we look at this and we go, fine, B and C. B is a double bond, C is a triple bond. Okay, now, here, this is actually about how reactive the molecules are. Also, when we look at this particular alkyne, okay, so we've got our carbon, and then we have our triple bond, carbon, hydrogen, and then the hydrogens look like this. Okay, we're okay with that. The alkene looks like this. Now, I told you that for our purposes, we consider the hydrogen-carbon bond to be non-polar, but it isn't actually, it is polar. So I've got to look at, with these bonds, I've got to look at the symmetry of the molecule, okay? The alkene, as I've written it here, is a little more symmetrical than the alkyne, because the alkyne has got this hydrogen part at the back here, and then we've got this big hydrogen part over there. So the alkyne tends to be more polar, okay? It's not very polar, but it is a little more polar. So when we're comparing these, I can't go, well, the alkyne's going to have stronger London forces. There's no reason for it to have stronger London forces because if it's non-polar, it's non-polar, okay? And they're relatively the same mass, so that's not going to make a big difference. We're only missing one hydrogen. That's only one extra electron and proton. That's not going to make a big difference either. So actually, that doesn't make any sense. So this has to be on polarity. And I know now it becomes, but this is one of those things where the more questions you do, the better idea you get of what they're asking. So between the alkene and the alkyne, what we're going to say in our explanation, and this is where where you need to pay attention to what I'm doing with you, okay? Because with the explanation, what we're going to say is the alkynes tend to be more polar, okay? Why? Because of their triple bond, okay? Why? Due to the triple bond. So we've now got why it tends to be more polar. Because it's more polar, okay, tend to be more polar. This means, okay, that the intermolecular forces, and I'm just going to write IMF for short to save time, the intermolecular forces will be stronger. Okay? So my intellect, not stranger, stronger. I've just realized that looks like stranger. This is why your handwriting is so important. Stronger. Not sure that helped, but let's just go with it, okay? So the intermolecular forces will be stronger, or will tend to be stronger, even if it's just a little bit. But now minus 23 and minus 48 is quite a big difference. It's 20 degrees. That's a lot, actually. Think about the difference, how you feel when it's 20 degrees and when, well, hopefully none of you live anywhere where it's been 40 degrees, okay? That's horrible. So 20 degrees, that's a big difference. In fact, it's 25 degrees. It's huge. So the intermolecular forces will be stronger. Therefore, now what? You have to give this to me. More energy is required. Now, here's the big thing. Okay? So more energy is required to weaken the intermolecular forces. Write it again. I know it feels like we writing it over and over again, but we want to make sure the examiner knows we're talking about the intermolecular forces and not the bonds. Okay, therefore, more energy is required to weaken the intermolecular forces, and the boiling point is higher. Okay? You guys okay with that? This doesn't have much to do with the fact that alkenes and alkynes are far more reactive than alkanes. When we talk about reactivity, we're talking about breaking the double and triple bond, okay? Here, it's got to do with the intermolecular forces, okay? And it is a little strange, I just want to touch on this, that if you look at these, that your double bond has got a lower boiling point than your single bond, and that's simply because when we make a double bond, it makes the molecule a little bit smaller surface area, smaller intermolecular forces a little bit, it makes the intermolecular forces weaker, therefore it's going to have a lower boiling point, okay? Don't stress too much about those, okay? The point here is that the alkynes can tend to be more polar because of the triple bond. That's the important part here. It's about the shape. So this one is about polarity. We've already spoken about the London forces. Just means that this has those London forces, but because it's polar, the intermolecular forces will actually also turn into dipole-dipole. Okay, but they're very weak dipole-dipole. Very small difference. All right, grade 12s? Hopefully that's going to give you time to sink in. So think about that for a little bit. We're going to take a short break, and then we're going to hit you with a couple more questions, and we'll see how you do. Okay, grade 12s, let's hit this last part together, okay? So I have a quick question for you. I'm not going to give you a lot of time on this one. I want you to arrange the following substances according to increasing order of flammability. Now, we haven't dealt with flammability, but I want you to think about what it means if I say something's flammable and what that would mean for the intermolecular forces, okay? But I'm not going to give you a lot of time on this one. So actually, you're going to have to do this really quick. I want to know what goes into your head first. So I'm giving you 1 minute to do this one, okay? Are you ready? Have you got your pens ready? All right, off you go. Okay, grade 12s, how did you do? Now, when we look at flammability, this is the first thing we've got to consider. Flammability means how quickly will it burn, okay? This has to do with intermolecular forces as well as just the reactivity of the substances involved, okay? So when we look at increasing order of flammability, what we're talking about is from the least flammable to the most flammable, okay? And with a question like this, before you even consider anything about it, look at the information. So we've got ethane, ethane, methane, tetrachloromethane, bromoethane, bromomethane. First of all, the halogens will be polar molecules generally. That means the halogens will have very strong intermolecular forces. So I know that my original ones has got to come from this line, okay? Then we look at the others and we go, we've got ethane, ethane, methane. From what we've learnt about things, methane is the smallest molecule, so methane is going to have the smallest intermolecular forces, so methane has to go last. It's going to burn the quickest. Okay, so we know methane is going to go last, and there's 6 things, so I'm going to give that, I would put that number 6 in my order, okay, not that's a 6. The halogens we know are going to have to go somewhere between 1, 2, and 3. That means now I've got to choose between 4 and 5 for the ethine and the ethane. I consider what we just did in terms of the intermolecular forces, and we go, well, ethine has a triple bond. That's going to make it a little more polar, but it's got a triple bond. It's also smaller as ethine. Ethine is actually going to look like this, so we draw the structure, and we go ethine. Ooh, look there. It's not going to actually be more polar. It's going to be non-polar, and it's tiny, okay, compared to ethane. Because remember, with ethane, which I'm going to do over here, ethane has a whole bunch of extra hydrogens. Now, those extra hydrogens increase its molecular mass, but it increases its surface area, which means it's going to have stronger intermolecular forces, which means ethine is going to go at number 5, ethane is going to go at number 4. So we're all okay with that. Now we've got to make a decision between tetrachloromethane, bromoethane, and bromomethane. Here, this comes down a little bit to what you know about halogens and those sort of things, and we actually tend to use halogens in organic molecules as fire retardants. They don't burn very well at all because of the way they bond. Now, the more halogens we have, the less flammable the substance becomes. Okay, so tetrachloromethane has 4 chlorines in it. It has to be number 1. Has to be the first one. It's the least flammable. When we look at bromoethane and bromomethane, this is ethane, this is methane. So we go, okay, ethane's got a bigger surface area than the methane. Both of them have got 1 bromine, so that's not an issue. Ethane's bigger than methane. That means ethane has to have a bigger surface area. If it's got a bigger surface area, then it's got stronger intermolecular forces, lower flap. It's not going to boil or react as easily. So that makes that number 2, which then means bromomethane must be number 3. Okay, now I gave you a minute to work that through, and it's taken us about 3 or 4 minutes to talk about it. Guys, be careful with questions like this because they look easy. They look like, oh, it's easy, we can just, but be careful at what they're asking you. You've still got to be able to think it through, okay? And sometimes they're going to be a little mean and they're going to ask you to explain, so be careful, okay? You ready to tackle one more question? I'm going to be nice this time. I'm going to do it with you. So, if we look at the last question, it looks a lot more complicated than it is, but it's really not. Says to us, haloalkanes play an important role in the chemical industry. The following tables can be used to compare the boiling points of alkyl halides. You know them as haloalkanes. It doesn't matter what we call them, with each other. Now, before you even start the question, you do what I said earlier. You say, okay, let's think what we're doing here. This first table is chloromethane, dichloromethane, trichloromethane, tetrachloromethane. So what we're actually doing in the first table is they're all methane, so there's only one carbon in them, but we keep adding in more chlorine. So we're increasing the number of halogens attached, okay? So that's what we're doing with the first one. In the second table, we've got fluoromethane, chloromethane, bromomethane, iodomethane. Okay, still one carbon in each of them, but I'm changing the halogen that's attached, okay? I'm changing the halogen, and in fact, I'm getting bigger as we go down, because these are the halogens from group 17, and the smallest is fluorine, the biggest is iodine, and in fact, their boiling point increases with that. We look at the haloalkanes. As we increase the number of halogens, same halogen, we increase the boiling point. So, use the information in the tables above to answer the following questions. Write down the formula of 2 haloalkanes that are dangerous according to you at 25 degrees Celsius. 25 degrees Celsius is important. That is room temperature, okay? When we look at the table and we go, okay, boiling point means it's going from a liquid to a gas. If their boiling point is lower than 25 degrees, at 25 degrees, they will be a gas. So that's that one, that one, that one, and that one, okay? We've got chloromethane twice, and now they only say write down 2. So I can choose any 2 of those, the chloromethane, the fluoromethane, or the bromomethane. But what would your answer be? You can't say here, now this becomes more of a general knowledge sort of question, so this isn't about intermolecular forces at all, okay? Yes, you need to be able to tell me that you recognize that they are, so you choose any 2 of the 3 we had, and we say, well, they're gases at room temperature, okay? So why does that make them dangerous? So that's part of it. They're gases at room temperature, which means they're easy to inhale, okay? So you would inhale them, you're going to breathe them in, but they are incredibly toxic and they are poisonous. So the point here is a lot of the halogens are carcinogenic. They cause cancer. But with these particular ones, it's about the fact that they are incredibly dangerous. They're incredibly toxic. They cause respiratory problems. And if you inhale enough, heaven forbid, okay, it can cause death. Even something like trichloromethane, which is chloroform, which they use as anesthetic, that's a cumulative toxin, so it builds up in your system, and you can overdose on it. It's actually quite scary what you can do in these things. And it can kill you, and it's not pretty. So it won't just make you fall asleep, it'll make you stay asleep, and that's bad, okay? Now, identify the trend in boiling points in table 2, give an explanation for the trend. So, we go back to 2, and we say, fine, the trend is this. Now we've got to look at them and go, well, now I'm using a different haloalkane every time, but remember what I said to you, we're going down the halogens group, so we're going down group 17, As we go down the group, we're increasing the mass of the halogen. And as we increase the mass of the halogen, the boiling point's increasing with it. So here you can't just say that the boiling point changes with a change in the halogen. That's not a trend. That's not telling me how it's changing. So a trend is, if this changes in a certain way, then I'll get an increase or a decrease. If I increase mass, I get an increase in this. If I decrease mass, I get a decrease in this. Trend means relationship, okay? So what we would put here is, as the mass of the halogen increases, let's say of attached halogen, let's put it that way, I think it's a better way to put it, of attached halogen increases. Writing too fast for the board today. The boiling point increases. Okay, that is the trend. Now, they want to know why. Okay? These are all haloalkanes. They are all polar molecules, so they have dipole-dipole forces. Okay? However, as the size of the halogen increases that we are attaching to the carbons, the surface area is increasing, okay, and the molecular mass is increasing. This increases the strength of the intermolecular forces. Thus, don't you just love these explanations? Thus, the energy required to weaken the forces increases, okay? So I'm going to put this here, okay? I'm going to put it at the bottom. Ooh, there we go. Come, say hello. This thing doesn't like me today, but we all know that's normal, okay? So, as the mass, and I'm going to do some shorthand here, okay, because we're going to run out of time. As the mass of the molecule increases, I'm going to put an up arrow, meaning increases, okay? As the mass of the molecule increases, the dipole-dipole forces increase. Okay, so we have stronger intermolecular forces. Therefore, more energy required to weaken the forces to weaken the forces. And boiling point, let's get rid of all my dots, there we go, boiling point increases, okay? Stronger intermolecular forces, bigger mass, bigger surface area. You could even talk about the fact that they become more polar, okay? And in fact, that's a big thing here as well with the halogens. So it's not just about their mass, it's also about the fact that as you go down the group, because they're getting bigger and the atom that's been attached is bigger, the dipole-dipole moment gets a bit bigger, okay? And that's fine. We're okay with that. But looking at the mass is a much better idea, because remember, fluorine is the most electronegative element that we have. So we don't want to start getting to that debate with this as well, okay? Now, quickly before I have to go. It says, describe the relationship between the number of chlorine atoms and boiling point. So what happened in table 1? As I increased the number of chlorines, the boiling point increased. So when we describe it, we go increase the number of Cl atoms and boiling point increases. Okay. Now, name the variable that was kept constant. What's the same between all of these? And there's only one thing, the number of carbons. Okay. So how does that happen? And what we have to have here is the number of carbon atoms must be constant. Because if I start messing around with the number of carbon atoms and the number of chlorine atoms, I'm changing two things. And we never ever do that. It's one thing at a time. Okay? Now, grade 12s. This section, the more questions you can do, the better you'll be at it. Because there's really a very limited number of ways I can ask this. Very limited explanations, very limited in where I can go with this. But you need to do problems. The more questions you do, the better you'll be at identifying it, okay? Now, next week, we are going to tackle reactions. Yay, I'm so excited because we're going to have lots to do next week. So hopefully we get in there, stick with it, grade 12s, practice, 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 and I'll see you next time.